This video is going to cover the chain rule. And so I'm going to do a little refresher on what a composite function is, exactly what it looks like, exactly how to define it, some of the notation around it. Historically, students find the chain rule extremely difficult. This is one of the harder, maybe the hardest, of the derivative rules to both remember and to apply correctly. So this is a very important video, and I'm going to go through it step by step. Now, to begin, let's talk about what is a composite function. A composite function is a function that can be broken into, well, more than one part, but it's when one function is embedded in the other. And so you might recognize this notation from earlier in the course. And this is basically saying that we're going to take the g function and then we're going to apply the f function to that g function. So the g function here is embedded in the f function. And that's what we mean when we say a composite function. Now here are some specific examples. So you can think of this as f of x, and the one to the right of the circle is g of x. I'm going to apply f of x to g of x, and so I'm going to write this. There's my g of x, and then just to be clear, I'm going to apply f of x to it. And then so this outer one, that's our f of x, right? F of x is x squared. G of x is the internal one, the kernel, 1 plus x to the power of negative 2. Similarly down here, notice that I've switched the positions of f of x and g of x. This time we're going to apply g of x to f of x. And it's not going to be the same thing. It's going to be different. So let's start off. We'll do it the same way. I'll write x squared. That's the interior function. And, or maybe what I'll do is this. I'm going to rewrite the exterior function, this g of x. And wherever I see x, I will replace it with x squared. And so we get x squared, power of negative 2 plus 1. And that's equal to g of f of x in this case. So that's a little review. And you can see that they're quite different functions, right? If I get rid of some of this, you can see that, you know, they're quite different. Now we need to introduce a new form of notation. So before we had the prime notation, we had prime notation. Prime notation, if we had f of x, that implied that its derivative was f prime x. And now we're going to introduce Leibniz notation. Why do we need Leibniz notation? More importantly, why do you need Leibniz notation? You need it because you're going to see it, and you're going to see it very often. And often textbooks prefer to use Leibniz notation because it's more specific and it makes it easier to communicate. Right? Here, you need to know that we're taking the derivative with respect to x. And that's easier when it's univariate. Just one changing variable, x. But it would be pretty confusing if we had more than one changing variable. And you'll sort of get a taste of what that's like when we look at implicit differentiation in Chapter 7. So you need it because it's going to give you some more detail. And also in this course, you're going to be tested on both, so you need to know both. Now, how do we write the derivative under Leibniz notation? So if we had the actual function is little f of x, under prime, we'd have f prime of x. Now we're going to write it like d. I can write it in a few ways. I could write it d f of x dx, or I could write it d over dx f of x. So that's how I would write the first derivative. Right, we'll talk about second derivatives later. That's how I would write the derivative of f of x. I'm going to use these d's. And so sometimes it's called differential notation. Right. I'm taking the derivative of the function f of x with respect to x. So how would I write these two derivative rules, the product rule and the quotient rule, using Leibniz notation? Well, what I could do is I could write d f of x. Remember, there's no primes in Leibniz notation. Dx, multiply this whole thing by gx, add f of x multiplied by d gx over d of x. And there's my product rule in Leibniz notation. I could do the same thing for the quotient rule. I've got d f of x over dx multiplied by f of x. You know, if I wanted to, I could write it like this, where I've just got df. Maybe in this case, it'll look a little bit nicer. I can get rid of the dot. Plus f of x times the derivative of g with respect to x. And the whole thing, well, the denominator, g of x, is still squared. Per usual, doesn't change, because of course this notation only affects derivatives. It's derivative notation. And so maybe I'll just come back to here, and I'll just say that I could write those ways as well, but I could also just write it as df over dx, like so. All right, so we spent all that time, we reviewed composite functions, we talked about Leibniz notation. Now we're ready to learn about the chain rule. So here's our function, big F of x. Now, as you know, we can divide this composite function into little f of g of x, right? And we've got g of x is equal to x squared plus 4x. That's our kernel, or our interior function. And f of x is what? F of x is just x to the 1/2, which of course is equal to the square root of x. Now, if we want to find the derivative of this thing, what do we have to do? Well, we're going to have to follow a recipe. I'll show you how it works. And in English, we want to find the derivative of the outside function. So that was f of x is equal to the square root of x, or x to the 1/2. Then we want to find the derivative of g of x. Right? We want to find the derivative of g of x. And finally, we want to multiply the two together. So we're going to get something that looks like f prime of g of x multiplied by g prime of x. And so let's do an example together, and let me show you what this looks like. Then we'll come back and we'll redefine the chain rule formally using Leibniz notation. Okay, I'm going to take the derivative of the outside of this function. I'm going to take the derivative of the inside, and then I'm going to multiply the two together. So the exterior is equal to 1/2 times 2x squared plus 4x, 1/2 minus 1. So I'm taking the derivative of the exterior. I'm not worried about what's inside those brackets. I'm going to take the derivative of the entirety of the exterior. And the interior is, well, it's 2x squared plus 4x. So I can apply the power rule twice, and I get 4x plus 4. And maybe I'll put brackets around that. And then now I'm going to take the exterior and multiply it by the interior. And I get 1/2 2x squared plus 4x to the power of what? To the power of negative 1/2 multiplied by 4x plus 4, the interior. So this is the derivative of the exterior, and this is the derivative of the, well, the textbook calls it the kernel. I like to call it the interior, but let's stick with kernel. Sometimes these functions can get pretty complicated. You can have composite functions with more than just two functions. You could have 3 or maybe even 4 if you've got some really complicated function. Now that's one way to find the derivative of a composite function. That's one way to apply the chain rule. Now I want to walk you through the Leibniz notation because it's going to be important for understanding topics in Chapter 7 and Chapter 8 and Chapter 9. And it's going to be important for you understanding topics in second year, third year, and fourth year. And if you didn't understand the chain rule the first time, or if it seemed a little bit weird to you, maybe this way will make a little more sense, a little more formally. We'll do it a little more formally. So the chain rule is written on the slide. I won't repeat it. One thing we can do in Leibniz notation is we see that if we've got, well, this should probably be something like f of g of x. And then you notice that this looks a lot like f of g of x, except we've got y of u of x. Y of u of x. And if we look to find the derivative of this, well, maybe I will leave it as y. If we want to find the derivative of y with respect to x, then we take the derivative of the outside multiplied by the derivative of the inside. So if I write, I'm going to write, let u be equal to the interior. So 2x squared plus 4x. Then I'm going to rewrite yx is equal to 2x squared plus 4x to the 1/2 as y of x is equal to u to the 1/2. And if I want to know the change in y with respect to x, that's equal to, well, take the derivative, oops, that should be d, the derivative with respect to u, excuse me, that's the derivative of y with respect to u. If I want to know the derivative of y with respect to u, I'm going to take the derivative of, again, I should change that or watch my notation here. I'm going to take the derivative of this thing with respect to u. And so I get 1/2 u to the negative 1/2. And I've also got this u function over there, and I want to know the change in y with respect, oops, excuse me, should be the change in u with the change in x. If I want to know the change in u with respect to x, I'm just going to take the derivative of u with respect to x. We get 4x plus 4. Now, notice up here, we're going to multiply the outside and, well, the kernel, and those are the derivatives of them. And so I've got these two derivatives. One is the derivative of the exterior, one is the derivative of the interior. I can write this dy over dx is going to be equal to, well, dy over du times du over dx. I've got 1/2 u negative 1/2 multiplied by 4x plus 4. Just make sure that that's legible. Now I'm almost done, but finally I'm going to replace u with u equals 2x squared plus 4x. And I've got 1/2 2x squared plus 4x multiplied by 4x plus 4. Now, as usual at the end of the video, I want you to solve a problem on your own. So here I have a composite function at the top of your slide, and I'd like you to answer the following 4 questions. So we can define ux as 1 plus 2x. That means that u of y is just going to be u to the 1/2. What's the interior function? Well, that's always the u of x, so that's going to be 1 plus 2x. And what's the exterior function? That's going to be, well, we can just write it as x to the 1/2. Or maybe I'll write it as u to the 1/2. Now, go ahead and apply the chain rule and find the derivative of this thing over here. Now you can press pause if you want to keep working at it. I'm gonna work through the solution here, and you can be welcome to work along with me. What's the derivative of y with respect to u? Well, if this interior thing is u, we're going to have 1/2 u to the negative 1/2. That's kind of like we had in the earlier example we worked through. What is du with respect to dx? Well, we've only got the 1x inside the bracket, so that's just going to be 2, right? Because we've got x 1 minus 1, x to the 0 is equal to 1. And then finally, multiply them both together. Well, I shouldn't say finally, but we're going to multiply the two of them together. And I want to replace the u with what it's actually equal to. U is equal to 1 plus 2x. And when I do that, these two canceled out. When I do that, I get 1 plus 2x to the power of negative 1/2. And that is the chain rule.